See, now the title I have here is more or less the title I was given by David. Is that your, did you make that
Yeah,
up
I
for
made
Barry?
that.
You did that all that by,
Yeah.
all by yourself?
Yeah.
Does anybody detect a difference between this title and what was listed in the program? What?
Physical.
Physical. Now well, no, I think it was physical. What was in the program? Was it physical or what did it say? Anybody have a program?
It says the architecture of fundamental theories, the idea of typicality.
Yeah, okay. I just wanted to, we're talking about fundamental physical theories. I'm sure David agrees with that. There are two parts here. Architecture, fundamental physical theories, and the idea of typicality. I'm not sure whether David intended them to be two separate topics or to be related.
I was giving you as many opportunities
I was
as
supposed to
could
choose.
to react, negatively to what I had said earlier in the meeting.
Okay, well, look, I tried to think of this as a unified topic, so I want to relate here, because of the title David gave me, typicality to the architecture of fundamental physical theories. And actually the talk will have three parts. And I'm going to begin and maybe motivate the whole discussion of typicality and fundamental physical theories by spending some time talking about the point of Bohmian mechanics. And I guess look in kind of simple terms. What I found is that even though the point of Bohmian mechanics seems kind of obvious, and David made it rather clear yesterday how it seems kind of obvious, it seems that a physics education is such that the obvious point eludes people. It's not simply that people say, no, I don't like the theory. I see the point of it. I understand why you want to have a theory like that. But really, I think physics should be different. I get the impression that a lot of people simply don't get the point at all. Why are we doing this? And though there may be no people like that here, I think it would be worthwhile nonetheless to spend some time on a very simple level on what is the point of Bohmian mechanics. First point of Bohmian mechanics would be that there are, as everyone here knows, issues with quantum mechanics. It's problematical. This is the wrong obvious audience, I suppose, to emphasize that with. Nonetheless, here are some nice quotes expressing this sentiment in rather different ways. Here is Einstein. He says, I too have many reasons to believe that the present quantum theory, in spite of its many successes, is far from the truth. This theory reminds me a little of the system of delusion of an exceedingly intelligent paranoia, concocted of incoherent elements of thought. My sense is this is right on target. Did anybody ever have that feeling about quantum mechanics? Did anybody ever not have that feeling? This, you'll notice, is in a letter. I don't think in publications you ever quite said anything that's dramatic. His qualms about quantum mechanics. Here's a much more tempered statement saying something very much in the same spirit by John Bell. Conventional formulations of quantum theory, and of quantum field theory in particular, are unprofessionally vague and ambiguous. Professional theoretical physicists ought to be able to do better. Bohm has shown us a way. A crucial point here is that for many people, including John Bell, the problem with orthodox quantum theory, and the reason they want something else, for example, like GRW or Bohm, is that they find the orthodox theory not too counterintuitive, that doesn't come to grips with it, but in a sense just too vague, unprofessionally vague and ambiguous. Now, in talking about the point of Bohmian mechanics, I want to go over about 7 different items. First, I want to review a little bit, and maybe in a sense, somewhat more detail than David did yesterday. Quantum mechanics, the target of the discussion. And then I want to focus on 3 intimately related but presented as separate sources of misgivings, confusion, tension, unpleasantness about quantum theory, namely issues of quantum properties, the need somehow for quantum theory about observers, the measurement problem which David talked about yesterday. And I want to emphasize that the source of all the trouble is a lack of an appropriate ontology, point out how Bohmian mechanics deals with that in a rather trivial way, and then relate, in fact, in detail, Bohmian mechanics to the problems I will discuss. That will be the first part of my talk. Let's see how that goes. So here's quantum mechanics. It has 2 parts. Part 1, part 2. Part 1 is the part most people like. Schrodinger's equation, basically. By the way, there's a kind of color scheme here which may not be used entirely consistently. But it's basically this. Blue is good, red is bad. Now on here the red, I'm not so sure I used it consistently. I don't mind. I like waveforms. So what is part 1 of quantum mechanics? It says, and this is basically you should think of this as more or less not for quantum mechanics most broadly understood, but let's say for an n-particle system or an n-particle universe, non-relativistic quantum mechanics, that covers a lot of physics. Similar story you could say for quantum field theory, but nothing much would change in terms of the issues and problems and foundations of quantum mechanics with quantum field theory. Let's think in terms of simpler picture, non-relativistic quantum mechanics. N-particle system, we say that system is associated with a certain space of states, a Hilbert space, and in the simplest realistic case, quasi-realistic case, that Hilbert space is given by functions, actually square interval functions, on the configuration space of the system of particles. So that a state is a vector, a wave function in that Hilbert space. It's a function of the configuration Q. It's a function of the positions of all the particles. I take it this is totally familiar to everybody. I say this is the simplest quasi-realistic case because I'm not taking into account with this particular statement here of wave functions which are just functions of configurations. Simple, complex valued functions of configurations. I'm not taking into account spin in that statement. There's no problem with spin, it's just that you have a little bit more abstract sort of wave function. The evolution is given by Schrodinger's equation. It's a very nice equation. It's written in blue in a fairly general form. And for more realistic systems, you have a Schrodinger Hamiltonian at the bottom, and everybody knows quantum mechanics has seen that before and understands well what that means. Those who haven't seen it before, what's written there won't help. And it won't matter. Schrodinger's equation is a very nice equation. That, by the way, though I didn't want to get into this, but I stumbled into it just now. That, by the way, is one objection, of course, to GRW, spontaneous localizations. You had a theory which involved some nice mathematics, a nice equation, and in order to deal with certain problems, you made the equation the mathematics ugly. That's not a fatal objection to that theory, not fatal at all, but I mean, even the authors of GRW theory would agree that not such a pleasant thing to have done. Okay, that's part one. Nice and simple piece of mathematics. By the way, what time did we start? 12? What, 5 after? Okay, good. And that clock is right now.
I think that clock is now running.
Yeah.
Okay, good.
We fixed it.
Okay. Here comes part two. And one of the crucial points here is that there is a part two. This isn't all textbook quantum theory. If this were all the students were taught, however much trouble they have understanding quantum mechanics, they'd have a lot more trouble. This is all they have. They'd have to read David's book. David. And as David once said, you have to really appreciate quantum mechanics from part one, and this is why he likes his theory so much. You have to engage in a lot of conceptual analysis, which I guess we're going to hear about this afternoon. Part two. Part two of quantum mechanics is the measurement postulates. It's impossible in one slide or 2 slides. It may be impossible in a reasonably sized book. It may be even impossible in a very long book to do justice to part two, to formulate it properly. Here is at least the general structure of part two. You've got the statement, first of all, that in addition to wave functions, we have observables. These correspond to self-adjoint operators on the Hilbert space. If you've learned about quantum mechanics, you might feel comfortable with such a statement. If when you learn about quantum mechanics for the first time, you feel comfortable with that statement, you're not a very curious student. You should wonder what the hell's going on. But this is not, I'll get to those questions in a minute. As mathematics, the statement that we have self-adjoint operators playing a special role is understandable. Self-adjoint operators, Hermitian operators, are a very clear mathematical notion. That they are, and somehow, in some sense, observables is not quite so straightforward to understand. But you just take it and you don't worry about it. Yeah?
Shelly, I just want to, I think, amplify what you just said. If it's not what you intended to say, tell me, but I think it is. The reason one ought to have, been given pause by a statement like that is I take it that the natural thought is...
The natural what?
The natural thought is that what's observable and what's not should be among the theorems of your...
Absolutely. Look, I want to talk about this in much more detail.
Not among its postulates.
Look, I'm doing a bad thing here. I'm always going off target. So this talk, I don't know how long it's going to end up being, but we'll be okay. Okay, so the observables are self-adjoint operators. You get used to that, which means you really lose sight, you become complacent, you lose sight of the fact that you don't know what the hell you mean when you say it. When we talk about the measurements of these observables, and you'll slide into talking about measurements of self-adjoint operators, and you think that's okay because you're measuring observables, so the word observable is doing a lot of work, and of course that's the thing you do to observables, you measure them. It's not the kind of thing you do to self-adjoint operators. Think about what's meant by self-adjoint operators. And there are rules which, for giving you the probabilities for the various results you might have when you measure a quantum observable. And the most compact statement of the rule is that the expected value of the result of measuring a quantum observable is given by the formula in the middle there. And from that formula, in fact, basically all the probability rules for the probabilities for the result of measuring a single observable follow. If you have a commuting family of observables, which would also correspond to something you could measure, lots of observables simultaneously, you could measure simultaneously because these self-adjoint operators actually do commute, then you have the probability formula for the joint distribution of all of these observables. And the most famous case of this is the case where the observables are positions or position operators. And the joint, they all commute. positions of the coordinates of position of a single particle all commute, all the coordinates of all the positions of all the n particles of an n particle system commute. So quantum mechanics supplies you with a probability distribution once you specify the state of the system psi of the probability distribution for the positions of all the particles, and it's given by psi squared, psi of the configuration squared, absolute psi squared, the Born rule. Okay. When you, as David described yesterday, perform a measurement of an observable and find a certain result, if you get the probability of finding that result, well, what I want to say is this. What happens to the state of the system after the result is found? The state will have collapsed to an eigenstate of the observable which you measured, so that if originally the system was in a state which was a superposition of various possible eigenstates corresponding to various possible values, so that in fact, according to the traditional story, you're not allowed to say there was any value for the observable beforehand, because the state was that sum. When the result alpha is found, a particular value alpha, the state of the system changes to the, I guess what's found here is the value A. The state of the system changes to the particular term in the sum corresponding to what you found. That's the collapse of the wave function, the projection postulate of quantum mechanics, and that, of course, occurs with the usual probability, the same probability that I sort of gestured at in the previous slide, coefficient squared, absolute value of the coefficient squared, the particular term in the sum. Everybody knows this, and in a nutshell, everybody here I think knows this, and in a nutshell, that's a sketch of standard quantum mechanics. Has two parts, a nice part about the evolution of the state, and a part involving special rules about what happens when you perform measurements. Okay. I had some quotes, like measure there, measurement there, cause of the other. Why do I have those quotes? Well, because as David said yesterday, and as I sort of begun to suggest today, and I'll talk about much more later, when we say talk about measurement in quantum mechanics, we don't really mean measurement. So if I'm not going to lie to you, I have to put on quotes. It doesn't mean measurement. Now, if we used a different word entirely, a word which had no particular misleading connotations, then when we talked about what happens in quantum mechanics, and we didn't say measure, but we used that other word, no people would say, I don't know what the hell you're talking about, because I don't know what situation you're talking about. When you use the wrong word, measurement, these people know what that word means, so they think they know what you're talking about, but they actually don't. David talked about that yesterday, and he gave an answer. Anybody remember what David's answer was? See, they didn't understand it.
I'm trying to remember my...
Yeah, your answer was actually what they mean. What they mean is what would have been called a measurement if we were talking about plasma mechanics, something like that. Which is certainly not appropriate here. That's sort of. Now let's focus on problem one: quantum properties, self-adjoint operators. What does it mean to say that the quantum observables or quantum properties correspond to or are associated with self-adjoint operators? The statement that they are self-adjoint operators is an odd statement. So the statement that they're associated with self-adjoint operators is a vague statement. What does that mean? Does it mean there's a one-to-one correspondence between observables and self-adjoint operators? But that would simply mean they have the same cardinality. Obviously, you mean more than that. Obviously, you mean something to the effect that the very nature of these observables, or these properties as properties, is connected with the nature of the thing as self-adjoint operators. Nobody ever says clearly what that connection is, and that would be something more precise discussion of the theory would require you to say, okay, what exactly is it about this self-adjoint, what is the connection between self-adjoint operators and physical properties? What do you really have in mind here? And maybe that can be done, and maybe in some 1,000-page books it has been done. It's not done in standard texts. Somehow many people think, look, it's just, okay, what do you mean? I mean, why can't, it's perfectly, there's nothing unclear about the statement properties of self-adjoint operators. I know what self-adjoint properties are. Self-adjoint operators are. I know what properties are. What's wrong with that statement? Properties of self-adjoint operators. You could have, of course, a statement whose words are perfectly clear, but when you combine them, it's not at all clear what you're trying to say. If I say the nature of reality is the empty set, everything in that statement is clear. I know what the empty set is, but I don't know what somebody is really conveying quite by saying that. Somebody could go on and say, no, the nature of reality is not the empty set, but the set consisting of the empty set. Still perfectly clear statements, but what the hell are you trying to say when you say that? Somebody might say, no, the nature of reality is the number 42. Everything's clear there, but what are you saying? Similarly here, the properties of self-adjoint operators. Okay, fine, tell me more about what you mean. That's the first problem. Second problem with the properties of self-adjoint operators. If we really mean properties, and if we really mean measurements of those properties, that means finding out the values that they have. That means they have pre-existing values. Number one, that conflicts with the standard law about quantum mechanics that properties don't have values unless the system is an eigenstate, of course, of that property, that observable. But second of all, we have theorems which say self-adjoint operators can't all have pre-existing values. The existence of pre-existing values is incompatible with the quantum probability rules. That goes back to, I'm talking about, of course, the no-hidden variable theorem. Going back to von Neumann, Bell, Koshin, and Specker, there's a long list. These are usually presented as saying that a deterministic formulation of quantum mechanics is impossible. That, of course, is wrong, because a deterministic formulation of quantum mechanics is possible and trivial. But what is correct is that you cannot regard quantum observables and measurement of quantum observables as revealing pre-existing values of those observables. So these are not properties in the ordinary sense of the word, and measurement of them is not measurement in any normal sense of the word. And there's a very strong tendency, nonetheless, to think, no, nonetheless, the properties of the system must be associated with self-adjoint operators. Those are the properties. That is something I call naive realism about operators. Taking operators as observables far too seriously.
So,
Yeah.
I mean, but self-adjoint operators and permission matrices are special in that they have real eigenvalues.
They are. So that is one of the things which at least helps you think that's a reasonable thing to do. But, you know, having real values, they're still operators. Look, you know what? Suppose they had complex eigenvalues. You know why measurements have real values? Because we calibrate the scale with real numbers. Because we'd be crazy to use complex numbers or quaternions to perform. What happens in the real world when you do a measurement isn't that real numbers point up. Physical states arise, pointers end up pointing. And if we want to describe what the result was, we put numbers. That's why the numbers are real, not because of any deep fact.
Well, yeah, so we calibrated quantum mechanics such that we choose this and it pops out real numbers.
It pops up real numbers because we want it to. Therefore, it would be reasonable that if, in fact, self-adjoint operators are going to have some good role in describing results of measurement in which the eigenvalues play the usual role, that their real is going to be convenient. But this in and of it, that's fine. But to say that self-adjoint are the properties themselves require, even to understand what that would mean is problematic. Yes?
Are you saying that there's an equivalent formulation of quantum mechanics that's isomorphic, where you don't use mutation operators, and then you spit out?
I'm going to tell you later on exactly what the situation is in Bohmian mechanics. So a similar story would apply to spontaneous localization, GRW, and I'm pretty sure a similar story would apply in Everett.
So this is the same basic idea that if you have two isomorphic mathematical theories, how realistically do you take the ontology of each of the things?
I think the theories in question here are not isomorphic, but we'll see what I think.
Or at least they one is a subset of the
Yes,
other.
that's yeah, absolutely. We get that. Here's Bell. A final moral concerns terminology. Why did such serious people take so seriously axioms which now seem so arbitrary? I suspect that they were misled by the pernicious misuse of the word measurement, quotes again, in contemporary theory. But here's a normal use of quotes. This word very strongly suggests the ascertaining of some pre-existing property of something. Any instrument involved playing a purely passive role. Quantum experiments are just not like that, as we learned especially from Bohr. The results have to be regarded as the joint product of system and apparatus, the complete experimental setup. But the misuse of the word measurement makes it easy to forget this, and then to expect that the results of measurements should obey some simple logic, in which the apparatus is not mentioned. The resulting difficulties soon show that any such logic is not ordinary logic. It is my impression that the whole vast subject of quantum logic has arisen in this way from the misuse of a word. I am convinced that the word measurement has now been so abused that the field would be significantly advanced by banning its use altogether, in favor, for example, of the word experiment. I would say if there's anything you guys, anybody here wasn't really totally familiar with issues and foundations of quantum mechanics and coming to this kind of, the most important thing to learn would be how right on target Bell was in emphasizing the devastating consequences of the misuse of the word measurement. Once you come to appreciate that, things become enormously clarified. Yes?
Do we mean the same thing with the word time before special relativity and after special relativity? Probably we don't. So what's wrong with a theory coming and changing the meaning of a term?
There's nothing wrong with it as long as you explain that you are changing the meaning and try to convey what the new meaning is. That doesn't happen.
Well, for Bohr it happens. It's the complementary to between.
There's a lot more explaining. Here's a good term, experiment. If you say, no, I don't want to use the word experiment because I mean something else and therefore I want to say measurement, but you agree that the conventional understanding of the word measurement is inappropriate, which everybody should agree, then it's your burden to explain why you want to insist on using a word with misleading connotations rather than using the word experiment. Yeah.
But is not a probability distribution built up by a series of measurements?
You do experiments, you get results. Whether, if you want, I would distinguish between a measurement of something, which means there was something to be measured. If I measure the position of a particle, I would say that as a matter of logic, that means the particle had a position beforehand. If the particle, for example, did not have a position beforehand, and I did this thing which was, quote, a measurement of position. I wasn't measuring the position, maybe I was creating a position. I was doing an experiment which produced an effect, but to call it a measurement position can only cause confusion.
Well, granted, but if you're making a series of measurements of identically paired particles and you're coming up with different results, does that mean you're not making measurements?
If in that series of experiments, those results don't reflect what was done beforehand, then you weren't measuring the quantity. You were just doing something which led to a stochastic result. Yes, Ken?
So maybe it'd be helpful to have a simple concrete case. Even in classroom, Suppose I give you the following recipe. Say, take a coin out of your pocket, flip it. Okay? That's an experiment. But I'm not measuring it. And furthermore, if I flip it over and over again, I'll get some statistics. And maybe I even think my theory ought to explain those statistics. But those flips are not, in any reasonable sense, measurements.
Ah, okay, I get it. So you're making a series.
So the idea of a measurement is a particular kind of interaction with a system that reveals a pre-existing value or something.
Right.
And flipping a coin just does it.
Right.
Yeah.
Good. Would it be fair to say that regarding pre-existing properties, maybe your electron has a pre-existing property, but the thing that we call measurement doesn't reveal that, it produces something new, which is the joint, the joining of the measurement apparatus and its state, and it's something that you're not revealing pre-existing property, you're producing something new.
That would be fair to say. The only comment on that would be that's a perfectly fine experiment to talk about in connection with quantum mechanics. But it would be better not to call it a measurement of the position if there was no position beforehand. Because of the clear connotation of the measurement.
Well, I'm saying independent of whether or not there was a pre-existing position beforehand, even if there was, the act of joining a measurement apparatus to it would change its state.
It may or may not change its state, but the issue isn't whether it changes its state. The issue is whether that experiment you did gave you information about the state beforehand. Did it tell you? We usually measure something to find out something about it. I measure the number of people in this room to find out, not the number of people in the room which will be produced by my counting them, but to find out how many are actually here before I did it. I want to find out stuff about the world, so I look and see and find out. That's the way we normally understand measurement. And to the extent that it's not like that in quantum mechanics, it's better to use a different word. This is a simple point, I think. Okay. Next problem. What the hell is it? What are we doing here with a theory which has axioms about results of measurement? A fundamental physical theory shouldn't have measurement axioms because measurement isn't fundamental. Measurement is some kind of interaction between macroscopic devices, an interaction designed for a certain purpose, which should be analyzable in terms of the basic physics which governs everything else. There shouldn't be special rules for measurement. That could be theorems about what happens in measurement, which follows from more basic rules. Here's Bell. The concept of measurement becomes so fuzzy on reflection that it is quite surprising to have it appearing in physical theory at the most fundamental level. Does not any analysis of measurement require concepts more fundamental than measurement? And should not the fundamental theory be about these more fundamental concepts? More Bell. It would seem that the theory is exclusively concerned about results of measurement. And has nothing to say about anything else. What exactly qualifies some physical systems to play the role of measurer? Was the wave function of the world waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some better qualified system with a PhD? If the theory is to apply to anything but highly idealized laboratory operations, are we not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere? Do we not have jumping then all the time? This is a good statement of why we need a quantum theory without observers. What does that mean? It means a version of quantum theory which does not have axioms about measurement, a version of quantum theory which has, of course, implications about results of measurements, because we want to understand why measurements do come out the way they do in terms of our fundamental theory. But the axioms of the theory should not involve the word measurement or observation or anything like that. That's a quantum theory without observers. And that's the only kind of quantum theory I would take seriously. I would say that's the only kind of quantum theory Everett would take seriously. That was the only kind of quantum theory the two Davids would take seriously, Tim would take seriously, Einstein would take seriously, Bell would take seriously, Stephen Weinberg would take seriously, and I would say the majority of physicists who are not inclined to something like quantum information theory would take seriously. They want a quantum theory without observers. There's widespread agreement on this point, despite the many, many differences about what the best alternatives are, what the best kind of quantum theory without observers is. This is another important thing to appreciate. You want quantum theory without observers. This is particularly important in cosmology, where there is no outside observer. So for cosmology, we definitely want a quantum theory without observers. Okay. Of course, if you want a quantum theory without observers, you've got a certain burden. You can't then connect your theory to the things that physics is supposed to explain, our experiences, results of measurements, by appealing to rules about measurements, because you don't have such rules. So the theory better talk clearly about something else out of which we can make contact with measurements. So you might think that something, if you're going to have a quantum theory without observers, then it better be something clear in the world, in physical space, that the theory is about. Because it ain't about measurement. Okay. Another thing. If we're demanding a quantum theory without observers, that means there are going to be, as I said, no special rules for measurement. That means if we want it to be a quantum theory, which has Schrodinger's equation as a fundamental equation, that should always be satisfied. So what happens in measurement should happen as a consequence of Schrodinger's equation. As David described yesterday, that leads to the measurement problem. If you take Schrodinger's equation as universal, as absolute, and apply it in the measurement context to system and apparatus, and as David described yesterday, you get into a situation where the wave function of system and apparatus is in a superposition of the apparatus giving one result, with the pointer, say, pointing left, that's psi left, plus psi right, the apparatus pointing in a different direction. Or in the case of Schrodinger's cat, psi alive, psi dead, cat which is a lead, so to speak. Those were Schrodinger's words, so to speak. A dead and alive at the same time. Yeah.
Are you saying that, more simply, that in a good theory, the Born rule should be derived from something more fundamental, not assumed as an axiom?
I do think that, but I'm not saying that. I mean, I can maybe somehow it could be an axiom, but it shouldn't be an axiom about observation. So maybe that's a fine point. I mean, certainly I don't want a Born rule, which is a rule about what happens when you do measurements. Now, I don't know. You see, you could say, as in fact David described it yesterday, there was something like a Born rule put into the axioms of the fundamental dynamics of GRW. That's fine.
As long as it's not about, as long as you're not putting an interpretation about measurement directly in there.
No, if it's about the fundamental
As
dynamics.
long as it's about something precise, as long as it's about something, like Shelly, I'm sorry, I interrupted.
Go ahead,
Shelley.
David.
It was, the Born rule played the role of a probabilistic claim about how the precisely defined physical stuff evolves in time. Then I take it Shelley is saying, in a context like that, there's nothing wrong with it.
Yeah, but that's a nice question, good question. It's good to clarify that. Okay, so I don't think nobody here has any issue with the measurement problem. Everybody agrees it is a problem. I remember when David lectured a few years, it was about 15 years ago at Rutgers, on something he wanted to talk about yesterday afternoon, and hinted he would talk about, but he didn't get to it. He spent a long time explaining the measurement problem, and while he was doing that, I was wondering, gosh, he's going so slow here. What's going on? And he later regretted the fact that he went so slow. He went so slow that people actually understood what he was saying so much that they went off the rails and everything, they went ballistic. The physicists. And the mathematicians who were observing the reaction of the physicists also had a real lesson. Because up until that point, they did not realize how physicists could react to things which seemed totally obvious, but would resist and resist and resist. Do you remember that, David?
Oh, yeah.
let's come to the subject of ontology. If measurement is not going to be, an observation are not going to be fundamental in your theory, something better be, the theory better have an ontology. Otherwise, I don't know how things are going to get off the ground. So again, what is missing? What was the problem? Basically, in all of the things I mentioned before, lack of a clear ontology. Clear ontology which is adequate, that does the job, makes correct predictions, and explains observed facts. That's what you need to have. Maybe it's hard to have such a thing, but that's what it would seem that you need. The hidden variables theorems would have suggested it would be really hard to actually come up with something. Maybe you don't need something really exotic. The hidden variable theorems were of such a robust character that they seem to rule out anything, no matter how exotic. That's why the whole question of looking for an ontology, particularly one for which the dynamics would be deterministic, was, deemed to be hopeless. The hidden variable theorems seem so utterly conclusive, and were so broad and general, they seem to rule out any possibility on any level. Planck scale doesn't matter. Let's talk a bit of, okay, so let's see, let's come to Bohmian mechanics and see how all of this works out in Bohmian mechanics. It better have an ontology, and of course it does. What's the ontology? Well, first of all, it's got the wave function, the usual wave function of quantum mechanics, and it's got something else. And the something else is the most obvious thing in the world to have, in the sense that to say that when you're, for the wave function of a system of particles, you actually have particles, things with positions, does not require an enormous amount of imagination. To get the essence of Bohmian mechanics to say that particles means particles. So that the state of a system in Bohmian mechanics is given by its wave function, together with the actual positions of its particles. Q1 through Qn, the positions of the n particles which form a configuration Q. If you take that seriously, you're almost at Bohmian mechanics. The crucial idea here is that you really have particles. You're not afraid of the word, you're not afraid of the concept, you take it seriously. That's not a theory, that's just an ontology. Theory requires some dynamics. What are the dynamics? Almost as obvious. Okay, so you stay with Schrodinger's equation. You don't change the evolution of the wave function. It's the same wave function and the same evolution for it. On the bottom, you have the extra equation, the guiding equation, the evolution equation for the positions of the particles. The velocity, it's a first order equation, not a second order equation. It involves first derivative with respect to time, not second derivative with respect to time. It involves fundamentally velocities, not accelerations. The q dt, not d2q dt squared. 1 is simpler than 2. In that sense, it's simpler than Newtonian. In that sense. And on the right-hand side, you have some,
Sorry, yesterday you mentioned in one of your comments that people objected to this blue equation because it was something, I think what you said was something like it was viewed as being something on top of the normal dynamics, an additional thing thrown in. But then your comments seemed to indicate that it wasn't really thrown in on top of. Can you clarify?
No, what I said yesterday, and this is a common objection to Bohmian mechanics. People object, but in this theory you need this crazy pilot wave. Lots and lots of popular books. You just pick up a popular book on quantum mechanics. If it says anything about Bohm, it'll have that objection. But they had to introduce this funny the pilot wave, or they had to introduce this funny quantum potential, or something like that, which is the same thing that's more or less the same as a pilot. There's a little different flavor there. I mean, nobody said anything about quantum potential here, and if nobody raises a question about quantum potential, we won't go into it, because that's another story. Now, why do people say that thing, that strange new thing which is supposed to be introduced, the pilot theory, is the thing that is not introduced? That's the thing which is common to almost all versions. That's just the wave function. That's not the new thing, that's the old thing. What's introduced is the positions of the particles. Now that is so trivial that it just sails under the radar. It doesn't even register with the people who are writing about it in popular accounts. that you're not introducing some exotic new thing, a pilot wave. That's the usual wave function. But you're giving that wave function a role on a different level than it has in orthodox quantum theory. In any version of quantum theory, the wave function, well, let me be careful here. In almost any version of quantum theory, and certainly in textbook quantum theory, the wave function has a very clear role. The role is to govern the results of measurements that's conveyed in the measurement axioms. In Bohmian mechanics, the measurement axioms are thrown out. That means thousands of pages which would have to be written to make them precise. You don't need them. Or the 2 slides you don't need. You just have one extra equation, the guiding equation. Instead of the measurement axioms, one other axiom, the evolution equation for the basic variables for the positions of particles. Yeah?
So it's clear that you introduced the positions of the particles as a new ontology.
Right.
I think following up on the last question, the question is the guiding equation something that follows from introducing the positions of the particles and the Schrodinger equation?
Certainly not.
Deductively?
Certainly not. Now, in some accounts, and Michael Kiesling has a very nice paper called Misleading Signposts, the Broglie-Bohm theory, or something like that, where he attacks the widespread presentations and a lot of papers in which people present Bohmian mechanics as following from Schrodinger's equation once you rewrite the form. And this is all very misleading. No, it doesn't follow as a matter of logic from Schrodinger's equation that you have a guiding equation.
So the guiding equation really is a new piece of the formalism which is introduced in the same way as in the old interpretation that the Born rule is a new piece of the formalism that's introduced.
It's a new piece of the formalism, absolutely. It's a new law. Absolutely right.
But the confusion is that it's not the pilot wave which is the new thing. That's just the wave function that's always been there.
Absolutely. The new thing is positions of particles. If you have particles with positions, which you didn't have before, you better have a law for them. If you didn't care how they behaved, what's the point of introducing them? Yeah.
Okay, so I might just be confused here, but it seems like there's some difference, or there's something new in the way the top bit of the formula, it's formally the same as it was before, but something's changed in the sense that before the wave function was standardly interpreted as representing the physical state of the system. That's why if it was in a superposition, there wasn't a fact of the matter about where exactly the particle was. And now we're not interpreting it in that way anymore because
Absolutely.
the ontology has been put in by hand.
Absolutely right.
And so the wave function, we have to interpret it as representing something else. And maybe that's what the people are getting at when they say, well, this is new.
You're giving them too much credit, I think.
I'm just trying to reconstruct it.
Let me make a remark about how people understand the wave function and how standard physicists understand the wave function. They don't agree with each other, and they don't agree with themselves. They're not quite sure how to think about the wave function. They don't know whether it's objective or subjective. If you look at any of the polls, for example, quantum information theory people are inclined to think of the wave function as simply representing information, our knowledge of a system, and not the objective property of the system itself. And many others would say, no, it must be an objective property of the system. How could you have interference otherwise? And I'm sure most individual physicists oscillate between these two things. On the one hand, it's a probability wave. That sounds a little bit like information, just what we know. That's why we collapse the wave function, we get new information. But it interferes. It seems, we call it the state of the system. It seems like some real thing. It's not as if people have any clear idea about the status of the wave function. Quite the contrary. Here's the change. In Bohmian mechanics, the status of the wave function is reasonably clear. At least it's so clear that you have to take it seriously. And one of the most common objections to what the Bohmian mechanics is that you have to take the wave function seriously in Bohmian mechanics. Okay. Good. Yeah. a word about, even if it doesn't follow as a matter of strict logic, the guiding equation doesn't follow as a matter of strict logic from Schrodinger's equation. And it certainly doesn't. One might still be curious about how you arrive at, or could guess, the guiding equation as a new law. David, yesterday, mentioned one rule. I will go back and explain it. look at that equation, you see there's something redundant in that equation. Namely, you have this psi star in both numerator and denominator. It should cancel. So why did I write this in such a redundant way? More complicated than necessary. I did it for two reasons. Written that way, the denominator, psi star psi, absolute psi squared, is probability, usual familiar Born probability density. Less familiar, but familiar I think to most people here. What's in the numerator is the quantum probability current J. We have here J over rho. We have here an equation involving rho. We have an velocity is J over rho. This equation has, as David mentioned yesterday, implications for the statistical analysis of this theory, which I'm not going to go into here at all. But you can well imagine that's true. That's one reason. That the right-hand side here is J over rho is very useful. Second thing is, if I didn't write it in this form with the ratio of two quadratic expressions in the wave function, if I just had a psi in the denominator and a gradient of psi in the numerator, suppose we were dealing with particles with spin. For particles with spin, the wave function is not complex value. It's spinor value. So we'd have a spinor valued object, many multi-component object in the numerator, and a multi-component object in the denominator. It's not at all clear what would be meant by the ratio of two multi-component objects. And even if we had just a single multi-component object, it's not at all clear what it would mean for the velocity to be a multi-component object at all. I mean, you know, X, Y, and Z components are fine, but not spinor components. It wouldn't be at all clear what this equation meant for spinors. But if I didn't have the quadratic expressions. With the quadratic expressions, the numerator and denominator can be understood in the conventional way with the products of numerator and denominator, meaning conventional spinor inner products, so the spinor and the free inner are summed over, and you get an equation so that you get an equation which makes sense for particles with spin, so that the incorporation, in order to incorporate spin into Bohmian mechanics, what you must do is, in essence, absolutely nothing. The thing you naturally write down, you write it down in this way, already deals with spin. I mention this particularly because another common objection to Bohmian mechanics is it can't cope with spin. And it's not the case that it can cope with spin by doing some complicated thing to deal with it. Although you might get that impression from Holland's book, where in dealing with spin, he spends about 100 pages trying to cope with it. In order to deal with spin, you don't have to do anything. Good.
Shelly,
Yeah.
I'd like to say that's a place where you could develop different versions of Bohm's theory, and you're saying that the version that deals with spin this way is the cleaner, better, simpler way of doing it.
That's actually what has happened, right? Absolutely. You should be a little puzzled about how it's all okay. You take it as something to look into further, because we don't have time to go into the details of why no problem with spin anymore. Here is what I consider the most elementary way of arriving at the guiding equation. That equation on the bottom, new equation, arriving at it, guessing it from what you have already. Most of the ways of guessing involve examining Schrodinger's equation, taking hints from Schrodinger's equation, like dividing up the Schrodinger current J by the Schrodinger probability, the Born probability rho, since J is rho V is J equals rho V is a very common formula from classical physics, from multivariable calculus, whatever. Everybody knows J is rho V. It doesn't require a lot of imagination to say V is J over rho. You've got the guiding equation, no imagination. But that requires Schrodinger's equation. Even more simply, before anybody had Schrodinger's equation, we had the de Broglie relation. I don't want to explain the de Broglie relation here. Those of you who know the background and know the basic physics know the de Broglie relation. P equals h bar k. Momentum, mass times velocity, is the wave vector, h bar times the wave vector k. On the left, we have something involving velocity, particle property. On the right, we have wave property. This is an equation which says the velocity is expressed, given by some particle property, the wave property, the wave vector. That makes sense for plane waves. If you ask, what should that mean? What should that generalize to? For general waves, general wave functions, the wave vector that you have for a plane wave should be replaced by a local wave function. That's a local wave vector. A local wave vector amounts to the gradient of the phase of the wave function, the gradient of s. You get an equation, velocity is the gradient of s over m, just from p equals h bar k, understanding the right-hand side in sort of the obvious way. And this is an equation equivalent to that equation. So even before, so just as in one of Schrodinger's derivations, and in many textbooks now, maybe in all the textbooks, you arrive at the Schrodinger equation. You guess the Schrodinger's equation from playing around with the de Broglie relation p equals h bar k. Even in an even more elementary manner, you arrive at this equation, the guiding equation, from just looking at p equals h bar k. So that is why I like to say that Bohmian mechanics is a version of quantum mechanics involving the obvious ontology, particles with positions, evolving the obvious one. And what would it be natural for a rational physicist and a rational physics student to conclude about that Bohmian mechanics at this point? I think the only conclusion one can come to is that, okay, you have some funny theory about particles moving in a certain way, but it has absolutely nothing to do with quantum mechanics. Yes, you've got Schrodinger's equation maybe, but this has nothing to do with the predictions of quantum mechanics. It conflicts with all the predictions. Because after all, how could physicists in generation after generation told student after student after student that something like this isn't anything like a deterministic reformulation of quantum mechanics is impossible, that you can't get around the strictures of uncertainty principle or any of the rest, that you can't do anything like this, that you could do it, how could it be today that you could do it in such a trivial way? That's just not plausible, it's not believable. So the rational student would have to say, no, obviously this doesn't work. I would certainly have reacted that way. I think it did react that way. But the fact of the matter is, it does work. One of the most common, another very common objection to Bohmian mechanics nowadays is that who cares about it? It makes the same predictions as orthodox quantum theory. So now the objection is that it does work. Works too well. The very same people used to say, how can you even think about such a thing? Bell showed such a thing couldn't possibly work. You've all heard that. Okay, here are the two slit trajectories, which are nice. They're good to see. They somehow show that, well, why are there lots of trajectories? Because there are lots of, I should emphasize, although it's clear to everybody, and David made it clear yesterday, I'll say it again, the theory is totally deterministic. If you specify the initial wave function and the initial positions of all the particles, everything is determined. 100% deterministic theory in that sense. So, if I specify initial position, the initial wave function, the usual two-slit kind of wave function, and the initial position of it's a single particle issue here. One particle specifies its initial position in the slit, the full trajectory will be determined. So here we have lots of trajectories depending on what the initial position, choice of initial position was. We choose the initial positions here more or less uniformly in the slits. You see that things remain more or less uniform until you reach a point where you would imagine that the two components of the wave function, the upper component and lower component, start to overlap, start to interfere, start to introduce what would be normal, what we would call an interference pattern in the profile of the wave function, where that you see that interference pattern, where there would be that interference pattern in the profile of the wave function, you see an interference pattern in the array of trajectories, so that the trajectories start to clump up where the wave function is big, where you have constructive interference, and sort of avoid places where you have destructive interference. So, as Bill said, is it not clear from the smallness of the scintillation on the screen that we have to do with the particle? Send in particles one by one. You see dots arriving at the screen one by one. Dot here, then dot here, then dot here. But they build up into a pattern. as we all know. And is it not clear from the diffraction and interference patterns that the motion of the particle is directed by a wave? De Broglie showed in detail how the motion of a particle passing through just one of two holes in the screen could be influenced by waves propagating through both holes, and so influenced that the particle does not go where the waves cancel out, but is attracted to where they cooperate. This idea seems to me so natural and simple. To resolve the wave-particle dilemma in such a clear and ordinary way that it is a great mystery to me that it was so generally ignored. And I think it is a mystery. It should be a mystery. There is another surprising feature about the two-slit experiment. Really surprising. Namely, when you look, you destroy the interference pattern. If I, as you all know, set things up in such a way that I can detect, either by sending in photons or whatever, which slit the electron went through, to try to catch nature in a contradiction, as Feynman said, the interference pattern goes away. You might want to think this would be a problem for a Bohm. What's particularly nice is if you actually try to honestly analyze what's going on in this situation within Bohmian mechanics, you see and understand clearly and deeply exactly why that was absolutely right. Why any way, any attempt, not any attempt, any successful attempt, anything that would work, would give you the information on which way the particle went, must inevitably, within Bohmian mechanics, destroy the interference pattern. To some of you that is clear, to most of you that is not clear. To get a real understanding of Bohmian mechanics, you should look at that and try to understand first for yourself, without looking at any written sources, how that comes about. I would say I could call it a homework exercise. It's a difficult one. See if you can do it. Figure out how Bohm explains that. Then you could peek. But then you really understand something. Okay. Let me go into some detail about what the implications of Bohmian mechanics are. Some of these implications are trivial, some are not. As David said yesterday, that you have familiar macroscopic reality, that you can have potential for pointers to point, is kind of trivial. You got particles with positions. You shouldn't be too surprised if particles with positions could come together to form things like pointers, which will have orientations. There's no fundamental, no conceptual problem about why you could have familiar macroscopic reality once you have a particle ontology. Or any other ontology too. It's just only a question of physics, of understanding why quantum mechanics, understood in a Bohmian way, is such that particles do hold together to form solid objects. But that's a question of physics, it's not a conceptual issue. Not so clear is where the quantum randomness comes from. Because the theory is totally deterministic. So where is there room for quantum randomness? But as David suggested in the first 2 days and also suggested yesterday, there is room for quantum randomness, just as there's room for randomness emerging in statistical mechanics from even a totally deterministic concept. Now this is not a simple story. There's a lot to think about here. David said a lot about it. There's much more to say. It would be impossible to go over, give you any details now. But quantum randomness emerges in Bohmian mechanics. And again, in an extremely compelling way, even in such a way that you obtain absolute uncertainty. So that the uncertainty principle of quantum mechanics cannot be overcome no matter what technological innovations occur in a Bohmian universe. So Bohmian mechanics shows more clearly than any version of quantum mechanics, I'm almost inclined to say, how quantum uncertainty is built into the core of quantum mechanics. That's not at all incompatible with an underlying determinant. Also notice that in the formulation of Bohmian mechanics, there were no reference to operators as observables. Operators as observables played no role whatsoever. Operators played a role, but that's natural. Operators are mathematical objects, and whenever you're doing mathematics, you're probably using operators in some form or another. And if you're talking about linear dynamics, you're going to have linear operators. So in Schrodinger's equation, you had a linear operator on the right-hand side. H applied to psi. H is a linear operator. So you've got an operator, but there's nothing puzzling about that. If you've got a theory, you've got equations, you probably have some operators. But operators as observables are not part of axioms of the theory at all. They wouldn't be in a quantum theory without observers. And yet, when one analyzes, when one applies Bohmian mechanics to the experimental context, when one sees what Bohmian mechanics would happen to well-defined laboratory experiments, what would happen in well-defined laboratory experiments, operators as observables emerge in exactly the way, the textbook way, as the most compact description of, as a compact mathematical description of conveying the statistics for the results of the measurements. And in the most general setting, what emerges is positive operator value measures, POVMs, which people in quantum information theory like to talk about. These emerge with absolute clarity as compact objects, conveniently conveying what's most important about the experiments, the statistics of the results. And this includes, when I said exactly, this emerges exactly according to the textbook rules, I meant to include that collapse of the wave function also emerges exactly as described in the textbooks. Wave functions of systems collapse in Bohmian mechanics. This exactly, when you do measurements on those systems, exactly in accord with the measurement postulates part 2 that I had before that I criticized. In Bohmian mechanics, part 2 emerges as theorems, not axioms, but theorems. You might wonder, how could it be in a theory in which the wave function, Schrodinger's deterministic wave function evolution is absolute, that it could be a theorem that wave functions collapse? For that, you have to pay careful attention to two kinds of wave functions which are relevant in quantum mechanics, I would say, and particularly in a Bohmian universe. There would be the Bohmian mechanics describing the wave function for Bohmian mechanics of the biggest system relevant, say the universe. I guess it's okay to talk about the universe at a summer school on cosmology, and the wave function of the universe. That, in a Bohmian universe, will be governed by Schrodinger's equation. And then everything that happens in that universe will be determined by that wave function and the motion of the particles of that universe as arising from the equation of motion. And therefore, one's not free to impose any additional rules about what would happen to a subsystem. What happens to a subsystem has to arise as a consequence of what happens to the whole. So in particular, it's not even clear a priori what would even mean that a subsystem would have wave functions, what would mean by a wave function of a subsystem. But when you think about it, you find there's a very natural meaning to the wave function of a subsystem in a Bohmian universe. That the wave function of this, you find that the wave function of a subsystem in general evolves, it's called a conditional wave function. This wave function of a subsystem evolves in a rather complicated way in general, but if you have a subsystem which is suitably decoupled from its environment, it will evolve according to the usual Schrodinger's equation, and in typical measurement situations, the wave function will collapse according to the usual rules. And I think Ward, in his talk, will talk more about conditional wave functions and apply conditional wave functions to problems of cosmology and inflation and so on. Can you say more detail? Okay, fine. I mean, there's another guy, Xavier Auriol, who's applying conditional wave functions in chemistry and in engineering to get good approximations for solutions to Schrodinger's equation. So people are using Bohmian notions to do standard physics nowadays. Yeah?
In cosmology, when you're talking about the Bohmian wave function of the universe, the largest relevant system, are you talking about just inside of the cosmological event?
No, I guess that's a good question. I think it would have to be even beyond. I suppose that question could come up in more detail. in the later weeks, and I'm sure that Ward will be happy to answer them. There could be some interesting questions there. I mean, usually it's got to be the whole kit and caboodle. The Bohmian wave function should evolve according to Schrodinger's equation exactly, only in the case of a closed system. So if there were a subsystem of the universe which is absolutely and eternally closed, but that's not what you're talking about.
No, I'm just talking about, should we regard the inside of the cosmological event horizon as a subsystem?
I don't think that will do for the purposes of the, it would be the wave function of the whole kit and caboodle.
Well, that would be an extension of this, so that if it's the whole thing outside of the event horizon, then by definition, inside of the cosmological event horizon would be a subsystem.
And you would probably then be talking about, from a Bohmian point of view, a conditional wave function.
Okay.
Yeah. Finally, you have, for this slide, you have quantum non-locality. Isn't one of the implications of Bohmian mechanics? That's a good thing, because if it didn't yield quantum non-locality, it'd be wrong, because we know that quantum non-locality is one of the most, well, a very firmly established feature of quantum mechanics, which doesn't depend on too many, it just depends on certain results of certain simple experiments, EPR type experiments, which tell us there's got to be quantum non-locality. That is an implication of Bohmian mechanics, and historically, this was discovered because Bell was thinking about Bohmian mechanics. He was thinking about it to understand exactly its relationship to the no hidden variable theorems, and he was trying to understand how the no hidden variable theorems went off the rails. How did they go so wrong? He had a perfect, clear counterexample of Bohm. He had these theorems. What gives? What was wrong with the theorems? And examining Bohmian mechanics, he noticed that it had a rather very strange non-local behavior was going on, and he asked, well, let's see, can we get rid of that non-local behavior in some way by coming up with something better? And what he ultimately showed was, no, you can't do better. That the experimental results of quantum mechanics show that this non-locality is unavoidable. Okay. I think it should be pretty clear now how Bohmian mechanics deals with the three main issues that I mentioned. It is clearly a quantum theory without observers, because observation and measurement do not play a fundamental role in its formulation. There is obviously no measurement problem because it has the obvious resources necessary for measurements to have results. Pointers point because you have particles and positions. The only reason you had a measurement problem was because you insisted that the wave function was everything. If the wave function is everything, you might have problems. You say, and the only reason there is to change its dynamics, or to say something of Redian. If you want to retain Schrodinger's equation, and you don't want to have so many worlds, you're going to have to go a Bohmian route, I'd say. I would call that a Bohmian route. I'll come to that in the next, what I mean by a Bohmian route in the next, what I mean in more detail the next time. And as far as quantum probabilities is concerned, that's what I referred to before. Even operators as observables emerge. That emerges as a theorem in Bohmian. Yeah.
Could you say a bit more about the quantum probabilities in the Bohmian picture? So
yes.
How the Born rule fits into the Bohmian.
Yeah. Let me give you. Remember Tim's talk? Tim talked a lot about Maxwellian probabilities and various derivations, and I might even get to something about that. You had probabilities there, Maxwellian probabilities. Describing random, we could call it random properties in a gas. Even though there was nothing in the framework under discussion at the time random in the behavior of the gas. It was assumed in the whole discussion that the underlying dynamics was deterministic. You should think of Born rule probabilities as roughly analogous to that. Now, there's a long, long story behind that.
But I mean, so in order to recover the empirical predictions of quantum mechanics, you have to assume that the distribution of particles, positions in space is equal to the square of the...
Okay, so on level one of an understanding, you say, let's just make such an assumption.
Right.
Then we can see how
But
everything
only,
goes.
only as an initial condition.
Okay.
No, David, let me say, no,
Because
I want to say a simple statement, not as an initial, as an initial condition for your system under investigation now.
Yeah.
And then you say, okay, let's see what would happen. So you take that as an extra rule. Then you say to yourself, but I can't have a rule like that. I want to know where it comes from. I want to have a deeper understanding of where all those probabilities come from. And then you go and you do an analysis. And ultimately it's going to be some sort of typicality analysis. And the typicality analysis is going to say that when you look at a Bohmian universe, it'll be a universe in which there's going to be an appearance of randomness governed by Bohr rule. Statistical patterns will appear in a typical Bohmian universe, just as there are statistical patterns appearing at a typical state of a gas in equilibrium. Now that's a long story, and it's controversial. We heard controversy in the last 2 days, first 2 days of the conference. And that wasn't even quantum mechanics. If the word quantum mechanics is used, there's got to be a lot more controversy. So that's something to really look into and come to understand better. It's a long story.
How does decoherence phenomenon fit into Bohmian?
In order to make the collapse secure, so that you don't have to worry about, because in terms of the wave function of the universe, it doesn't collapse. All its parts are there. And these parts can sometimes come back together and cause trouble. It's decoherence, which suggests that's going to be very unlikely. But that also is a long solution. There's not enough time to really convey properly how these things work. Those of you who know a good deal about decoherence understand already how it works. Those of you who don't understand much of the mathematics of decoherence, it would take too much time to explain it here, I think.
I'll talk about that this afternoon.
Good. But you should, those are good questions, and there are things I think that they're well worth your looking into. These are things which, look, a lot of things you hear in orthodox quantum theory, when you start to look into them, to try to understand them better, what you really understand is, you understand them less and less. It's not like that here. When you look more carefully into what's going on, you really start, you say, aha, now I'm really beginning to understand.
Well, what are the axioms in Bohmian mechanics?
They are what I wrote, and then there's going to be issues about some sort of statistical postulate kind of axioms, just as there were issues surrounding what David said. But if we were going to treat the notion of axioms in the same level and the same without invoking any real general double standard, then one would say the axioms in Bohmian mechanics, just like the axioms in classical mechanics and in statistical mechanics, are the dynamics, Newton's laws. Here the axioms are the Schrodinger's equation, the diagonal equation. Yeah.
Just maybe it'll be helpful for clarifying things to say, look, if you wanted to make the statement about Bohmian mechanics that's analogous to the kind of statement I was pushing about the statistics in classical statistical mechanics, what you would say is there's an additional postulate to the effect that this probability distribution over particle positions, given the wave function, applies as an initial condition, and then there's a theorem, unlike in classical mechanics, that relationship between the probability distribution and the wave function will be preserved by the dynamics. Now, so that's what would be analogous to the kind of view I was presenting of the statistics in classical statistical mechanics. Tim was trying to gesture at a different kind of view one might take of the probabilities in classical statistical mechanics, and there's going to be an analog of that in Bohmian mechanics, and that's going to be a somewhat longer story.
In any case, from any point of view, it's a long story, but it's one well worth looking into. Yeah.
Can you expand a bit on the relation between non-locality in Bohmian mechanics and locality in relativity?
How there's a tension between them.
Yeah.
This is a fact. I don't think there's time to do that.
Between what and what?
Between non-locality in quantum mechanics or Bohmian mechanics and relativity, which is a strong tension. That's what David was supposed to talk about yesterday. I mean, we can talk about that, but I don't want to talk. That's,
I gave you a title, you should have given me a title.
we talk about it privately. Yeah.
Could you say slightly more about the emergence of collapse and like bony mechanics? So you suggest kind of you introduce these sort of conditional wave functions as wave functions.
Yeah, let me see.
Does collapse emerge as a dynamical?
Yeah, here's the problem. I can't write.
Raise the glass.
It's very slow to raise it.
Just a heuristic picture of what?
No, okay, so how can we... Yeah, but,
So can you write on that?
I don't know how to make it work. Does anybody know how to make this work? Let me try. I'm afraid though, but let me try to say something. Yes.
Shelly, can you do just an on-off switch and maybe you can,
Maybe.
I don't know if it'll
I
work.
don't know, it might have to be connected, does it? I don't know. Give it a try, I don't know. Does anybody know this?
I'm also happy to do that.
No, that's non-trivial because it has to go through the electronics, so you have
I
to turn
see.
off one
So that's
thing.
not gonna
And I
work.
haven't
I
bothered
see.
to figure out how it works.
I see.
And
Okay.
Well, let me try.
our technical guy actually
Right.
stuck away.
Right.
Maybe it's not so bad. I need just a little bit of blackboard.
Well, why don't you just raise it all the way?
You mean you want to see my head? Is that okay?
Yeah, that's it.
Okay.
It's not working.
What's not?
You're not erasing the projection.
Close the laptop. I think
You have to write on
Yeah, close the laptop, Shelly.
Yeah.
What?
Close the laptop.
Well, what do you mean?
Just close it. That'll black the screen.
Is that?
Yeah.
Close it.
All the way.
Apple.
Philosophers. What can I do? Can I write over here?
Yeah, you can write
I don't
over
need a lot of room. You have a Bohmian universe. It's got a wave function, psi, which is a function of its configuration. Positions of all the particles. Configuration. You have a subsystem of the universe. That means a certain collection of particles. Let's call them the X particles. If you have a subsystem, then the overall, the total configuration can be split into the particles of the subsystem, which I'll call X, not just one variable, many variables, whatever, however, depending on how big the subsystem is. And then there's the rest of the variables Y. I like to use capitals for the actual Bohmian values, the actual values, because these are in the wave function, little variables, lowercase, argument in the wave function. We also have the actual configuration of the subsystem, the actual configuration of its environment, everything else in the universe, everything outside of the subsystem. First question to ask is, what should be meant, if anything, by the wave function of a subsystem, the X system? What are our resources? Well, if this is the wave function at a certain time, this is configuration, X and Y, that's all it is. Those are all the facts of the matter. So whatever the wave function of some subsystem is, it ought to be the final in terms of that data. Well, what would you guess it should be? Well, obviously you would think the wave function of the universe, capital psi, is going to play a role. I want a function of little x, so it would be good to put little x here. Or I should write this is capital psi, and Q is x, y, the function of x and y. So what should I do in the second slide?
I know what you
Yes! Shut up and calculate, David. What should I put in the second slide?
X.
What? X? Good, that's good. If I put x here, I got a function of x alone, that's what I want. That would be something, and it would be totally wrong. Now, what most people say is you somehow integrate over y to get something depending on x alone. That's a natural idea. Completely wrong. The right thing to do is to use another piece of the data, the actual configuration of the environment. You put that in. Then you think about that a while, and you realize it's just what the doctor ordered. It really corresponds exactly to what physicists were talking about when they talked about the wave function of the system. It does everything you want. The guiding equation for the subsystem involves this, what I just wrote there, is the conditional wave function of the subsystem. It governs the motion. It fits into a guiding equation of the subsystem of exactly the usual Boolean form. So this is indeed playing the role of the wave function of the subsystem. This is a thing which evolves in just the complicated manner I described, in appropriate situations evolving according to Schrodinger's equation, and in other situations collapsing according to the usual rules. To appreciate that a little bit better, it's good to think of a time-dependent situation. So the wave function, big wave function might depend on time. The configuration of the environment is almost surely going to depend on time. So there's a complicated time dependence there, sufficiently complicated that you should change to yourself, I don't have any clue about how that should behave. And that means it's something you have to look at, and when you look at it, what you find is what I told you. Yeah.
I hesitate to ask the question, but doesn't that sort of imply, I guess, sort of an ideal that there exists a y that's knowable?
No, nothing. I didn't say y was knowable. You don't have to know everything to know something. I just gave you a definition. Now you might ask, how could you know that thing? One way you would know it is if you knew capital Psi, the wave function of the universe, and you know the position of every particle in the universe.
If that means something.
I think it means something, but anyway, it's not going to mean anything too helpful here in the sense it means something, but you're not going to know it. You're not going to know all that. Nobody knows. We talk about wave functions of subsystems without knowing the wave function of the universe. This is a definition. But once something is defined, you can get a handle on what it is in a variety of ways. You could actually go back to the basic definition, or you can know it by its implications. It's relevant to the behavior of things. And by making enough observations, you might know what this object is without knowing everything. You better be able to do that, otherwise the thing is hopeless. This is the right notion nonetheless. I hope that answers your question. But to appreciate it better, take David's situation, or you know the measurement problem, and you know the usual measurement, the mathematics associated with the measurement problem. Ask yourself what will be the behavior of the conditional wave function in exactly that setting. You will have no difficulty seeing that what I said just comes right out.
But maybe there's one more thing you could say to give him a hint.
No, I don't want to give a hint. No, go ahead, David.
That in the case where how shall I put this? In the case where certain aspects of the y are kind of stable, okay, then it's really going to turn out to be the case that the conditional wave function is going to be the only thing going towards the future that's going to influence the motions of the x's. That's not guaranteed just by its
That's absolutely. I think that's a slightly different question, but that's an important issue.
Well, I thought he asked where the effective collapse comes from.
Well, yeah, he did, and that's going to be relevant to it. But actually, you don't even have to be thinking about that to follow up on this definition in the framework that you mentioned.
Right.
So it's really, all I'm saying is, in a certain sense, it's a rather trivial matter. It's not as trivial as it seems because of such issues as you raise, which is where decoherence might come in too.
Right.
Yes.
What do you do if your subsystem isn't a subset of the particles?
Yes.
Your subsystem isn't a subset of the particles?
Well, like what?
Like if you're looking at the fluxes, you mentioned.
Yeah, so you have to think about it. I mean, there are more this definition and this kind of splitting applies more robustly than I suggested. You might be able to think of situations which are really problematical and it doesn't apply at all, I'm not sure. And then I wouldn't know what really to say, nor would I know what to say in orthodox quantum theory, probably either.
In orthodox quantum theory, it like works miraculously well. You just like take the classical equations for the behavior of the circuit, you've got hats on it, and everything just kind of works.
Right. But insofar as those predictions of orthodox quantum theory work so well, our theorems from Bohmian mechanics, then you would try to understand exactly why in Bohmian mechanics in detail, how the objects which you were using in orthodox quantum theory fit in. But I have to look at a detailed situation to have a sense of what to say.
I think it's a very partial answer. I take it as far as the math system, although it really matters from an ontological point of view, that we're understanding the configuration coordinates of particles. I mean, I think the math doesn't really care. So
Math doesn't care.
Everyone needs a centre mass degree of freedom or something like that, that's fine.
That's fine. Oh, that's absolutely fine. Now, there could be situations, those situations would fit in fine. But there are other situations. I mean, even Bohmians are free to define objects which don't have a natural Bohmian foundation, but have a natural Schrodinger foundation. That's just mathematics, which we use when it's useful. So it would be interesting to see some concrete situations, the kind you're talking about. There might be something interesting to say about it. Okay. Yeah.
Could you say a little bit about how Einstein reacted to Bohm's
He
theory?
said it was a cheap trick.
And why? Like, what was his main?
Does that? Why did he say that?
Isn't that a good thing?
No, he didn't mean it as a good thing. Okay. First of all, several points. Actually, Einstein reacted several times badly to Bohm, but not to Bohm, but even worse to de Broglie. In 1927, Einstein himself proposed a theory very much like this one, but much more non-local, really problematical, so he decided not to publish it. Then de Broglie came up with his theory, this theory, 1927, which was much less problematical than Einstein's. Einstein should have been happy. Wasn't terribly supported then. I'm not sure why. Then in 1952, again, a similar cheap trick. Maybe one of the reasons Einstein reacted as he did was that he was much more ambitious. This isn't deriving quantum mechanics from something non-quantum. It's trying to formulate a version of quantum mechanics in as simple way as possible, retaining the essential, what might be argued to be the essential structure of quantum mechanics, Schrodinger's equation. Einstein wanted to derive Schrodinger's equation from a different kind of theory, a familiar kind of classical theory. So he wouldn't be too happy. Nonetheless, I'd have to say he should have said this provides a perfectly clear counterexample to all the things he's been arguing against. He didn't react that way. I don't really know. Another possibility, probably important, was the non-locality. Einstein probably recognized this was non-local, didn't like it. I don't know if he actually pointed to it, but I would expect he would have known it. He did know about Bell, so he didn't know the non-locality. It was inevitable. Tim?
No, I was just going to say, I don't know why that's not a perfectly comprehensible answer.
It is a comprehensible answer, but I think the other things I said, are also...
His main worry about quantum theory from the beginning was not, randomness or stochasticity. It was non-locality. That's absolutely clear. And Bell, you need Bell to say you can't get rid of it.
Right, but I don't want to suggest, maybe you do, but I don't want to suggest that was the only reason.
Okay. I think it must have been essential.
I'd say it was an important reason. Okay. Do you have a question? Okay, Bohmian mechanics versus Bohmian approach. Because one shouldn't come away thinking that the essential idea to a Bohmian approach is that you've got particles moving in exactly that way. That you have particles moving exactly that way is the content of the theory, Bohmian mechanics, that you saw. But it's not what's essential to the approach. Here is what I take to be what's essential to the approach. First of all, there's something like particles. There's a clear ontology, what I would call primitive ontology of the theory. The part of the theory, the elements of the theory which we are most interested in. Let me not go into any more detail about that now. Would be a long discussion. Primitive ontology and Bohmian mechanics are the positions of the particles with positions. Something that describes matter in space and time. Something that Bell called local beables. The local beables in a Bohmian approach do not have to be particles with positions. What's fundamental could be fields. What's fundamental could be strings. What's fundamental could be something else. What's fundamental could be flashes. God knows what. But there should be local beables. There's a state vector. When I talk about a Bohmian approach, it's an approach. It's a version of quantum theory, an approach to quantum theory, so it should be a quantum theory. So there should be a state vector in Hilbert space that evolves according to Schrodinger's equation. So you've got two things, wave function, Schrodinger's part. You've got primitive ontology, whatever it may be. Be flexible about that. Choices there, different choices will lead, of course, to different theories. And then you put the two together. And you put the two together in such a way that the state vector governs the behavior of the primitive ontology by means of laws. For example, the guiding equation. But they could be stochastic laws. The theory provides a notion, and this I haven't gotten to yet, but David talked a lot about it, a notion of a typical history. He didn't use that word so much. The theory provides a notion of a typical history of the primitive ontology, of the universe. For example, it can provide it by a probability distribution on the space of all possible histories. From this notion of typicality, the probabilistic predictions emerge. And in Bohmian mechanics, as David alluded to before, this probability distribution on histories of the universe would arise from a probability distribution on initial configurations of the universe, namely the psi-squared probability distribution on initial configurations of the universe. That's well-defined mathematically, and well-defined probability distribution. You use it to provide a notion of typicality, to say what's a typical behavior in the universe and what's an atypical behavior. And you say that the typical behaviors are those which have been explained. The atypical things are things you got to worry about. If it turns out your universe gives atypical behavior, your first reaction should be to say your theory was wrong. Something was wrong. It was bad. The predicted probability distribution of the macroscopic configuration at time t, determined by the primitive ontology, agrees with that of the quantum formulas. If it's to be a quantum theory, it ought to give rise to the quantum predictions. That's what I mean by a Bohmian approach. There's psi, there's some other stuff, the local beables, there's a mutual evolution, the Schrödinger evolution for psi, an evolution equation for the other stuff, maybe stochastic, a notion of typicality which allows you to extract predictions. That's basically what I would call a Bohmian approach. And if you leave out, by the way, and because we are working, I don't know how far I'm going to get. I'm not even going to finish 1/3 of the talk. So, think about that. If you leave out the quantum stuff here, you have more or less a rough sketch of what I would consider to be an appropriate architecture for fundamental physical theory. Now, a more detailed discussion of architecture of fundamental physical theory is the second part, which I'm not going to get through. There it was, the second part. And let me see if I can. There's some. One thing you want in a more general framework. So now, what do I mean in more detailed, but architecture of fundamental physical theory? there's no word quantum there. The world doesn't have to be quantum. So in the notion of the architecture of fundamental physical theory, there's no need that that theory be a quantum theory. Most of us probably believe that it should be a quantum theory because we think quantum mechanics is right. But I don't have quantum in mind here. What I've expressed here would be a quantum version of such a thing. But more generally, you should have something like ontology, adequate ontology, and the law for the ontology. There are all kinds of issues about what an adequate ontology is, but at the end of the day, I would say that an adequate ontology corresponds to a decoration of space-time. That means local properties, local things like particles and positions, world lines, things, local beables somehow distributed over space-time, so you could say what their values are at every location in space. Something which will provide you either through world lines or fields on space-time with a decoration of space-time. Stuff on space-time, lots of possibilities there. That's the sort of thing. Or in other words, a space of what Gelman and Harlow would call histories. Other people call histories, usually but not always, they have local histories involving local beables in mind. I would insist on the local beables. Yes?
I mean, Shelley, of course, this could open a huge can of worms which we can't get through, but maybe it's worth saying a little more about why you're going to dig in there, about why you're going to dig your heels in there, about why you're going to insist on the three-dimensional spatially local stuff, or 3 + 1 dimensional.
The short of it would be, which would be totally inadequate to say, I think your functionalism goes too far. But the better, nobody knows what that means. Now, let's take it on a naive way. What physics is, what I roughly would say the purpose of physics is to explain our experience. And that has to be taken with a grain of salt. Because physics is not going to explain our experiences. If by experiences you mean conscious experiences, because physics is not going to explain consciousness. But when we say we want to explain why we see certain patterns in the world, or why pointers end up pointing a certain way, what we really want to understand is why pointers are pointing that way. We don't expect to understand why we see anything, per se, why we have a conscious experience on it. But we want to understand why certain macroscopic patterns are playing. So the way I put it is, I think what we want physics to, what I understand explain our experiences to mean in a realistic way, and it's the only thing I can expect from physics, is to explain what you should naturally understand to be the macroscopic counterparts of our experiences. Tables, chairs, arranged in a certain way, pointers pointing. These are things on space-time, these macroscopic counterparts of our experience. And to understand them, one pedestrian way of understanding it is in terms of local beables out of which they are formed. Now, that is pedestrian, but almost all of decent physics of that form is of that form, and you got to do a lot of functional analysis. If you like that form, it'll be controversial. You would say, yes, but you should do that because that has certain advantages. But from a naive point of view, it's pretty clear why you might think this is the way you should go. Things are in space-time, that's what physics is about. You would say, no, you don't have to say that. Fine, then it could be a long discussion, but naively, it's clear what you want. Yeah?
So would you say that if you have a theory which has ontological properties like space-time and familiar things, and then you have a mathematical dual theory that makes the same predictions, but has a very different strange ontology, one of your principles is just, you favor the ontology that looks more like our normal space-time?
I would do that too. That's a principle Tim would definitely enunciate.
But actually, what you just said is a little bit incoherent.
No, my criticism of what he said would have been that it wouldn't make those predictions.
No, that's good. I mean,
but now elaborate on that, Tim.
What Shelley just said is, what do you mean by the predictions after? If the predictions are the locations of macroscopic objects in space, if you think that's the content of the predictions of the theory, not claims about your experience, red spot here for me now, or something about consciousness. If you think the predictions of physics are the macroscopic behavior of macroscopic objects in space-time, then if you have a theory that doesn't have macroscopic objects in space-time, it can't make the same prediction. You then need a different story about what you are predicting in the sense in which it's an equivalent theory.
I see what you're saying, but there's going to be a way of translating between the ontology of this other theory to the predictions, including macroscopic things
Well,
in space.
translating is
There's an isomorphism.
not every isomorphism is a translation. Okay, there might be all kinds of mathematical isomorphisms, but you need more than an isomorphism to be a translation, because part of the meaning, I mean, Shelly's claim is, part of the meaning is to talk about, as I say, macroscopic objects in space. If you have a theory that just doesn't have them, no translation of it, should say, according to my translation, there are such things, right? Because your theory says there aren't.
Can we cut this discussion? This is
Just
going to be
one
an endless
comment.
discussion.
There's an enormous difference between having them in the theory and having them fundamentally in the theory. Having them in the theory, the necessity of having them in the theory, it seems to me, is not in dispute. The question is, whether you have to have them at a fundamental level, or whether it's enough that it can be there at what you might call an emergent.
Right, that is the question, and that is an issue. And since you are a scientist, and you learn from experience that this is not going to be settled in 5 minutes, 10 minutes, or 10 years.
All the more reason to get on with discussing.
But most of the people here aren't familiar with that 10 years of discussion. Yeah.
Well, since this is a philosophy discussion, in some sense, I thought it was interesting that you said that physics will never explain consciousness for two reasons. One, because there's another type of Bohmian approach that attempts to do that, right?
No, I didn't give a reason for why physics. I just stated.
No, that's what I'm saying, is that you just
I just made that statement.
But I'm actually suggesting that there are a lot of people, especially in neuroscience, that would object to that statement. And
A lot of philosophers would too.
That physics could explain consciousness.
Of course they would.
So why did you say that?
Because I think they're wrong. I said what I think.
Hang on, Peter, distinguish two things. I'm not sure which Shelly meant. So one way of saying physics can't explain consciousness is a relatively strong claim, like science can't explain consciousness, machinery and mechanisms, all that stuff can't explain consciousness even emergently. That's really strong. A lot of people in neuroscience don't like it. Another sense in which you might mean physics can't explain consciousness would be physics can't explain consciousness for the same reason that physics can't explain digestion or the inflation rate. That's not physics' job, it's neuroscience's job. And I think in that sense, neuroscientists are run on board with it.
Thanks, David. Actually, I did mean both senses, but I really meant the strong sense too.
Yeah.
Well, one other wrench I'd like to throw into it, if I can, which is space-time is emergent, which is something that a lot of people are talking about.
I guess that's going to come up here. What about?
So you want to decorate something that's emergent?
I have had, when people throw around statements about emergence of space-time, when you pin them down, the story somehow tends to change rather dramatically. Now, because physicists have been trained on quantum mechanics, when they hear things they don't understand, they don't ask questions. Certain kinds of things that they sound really deep, like the emergence of space-time. I've been struck by that when I actually do ask them, say, look, I don't really mean that. I'm just saying stuff that normal physicists would say. I don't understand it at all. So that space-time can emerge from something different. It depends what the nature of something different is. For example, if you made a continuous space-time emerging from something discrete, that's not problematical. If you mean space-time emerging from something purely algebraic, I have no clue what you're talking about. Yeah.
And if you say a little bit more about why in the case of space and time you take it, that the explanation is going to have to be done in terms of at least some of the kind of things you're trying to explain. I mean, because it's not true in sort of science in general. If I want to explain X, I should take sort of something about X to be sort of a primitive part of that explanation. Often you sort of go to something else. Now, it's true that sort of philosophers have in mind this kind of distinction between secondary qualities and sort of primary qualities, which are going to be sort of location in space and time, things like that. But that's usually done in explanatory terms because they were convinced that those kind of things couldn't be accounted for except in their own terms, and that's what made them special. But now that sort of question is coming up, well, can they be accounted for in other terms that are sort of more primitive? And I take it you have some sort of view about why we should pick the box up.
If anybody could, well, look, if in economics, there are all kinds of frameworks in which we are not demanding a space-time explanation. But if we're trying to understand the behavior, ultimately, of the macroscopic counterparts of our experiences, which are patterns in space-time, then somehow space-time has got to get into the game. And if it's not there, in a sense, from get-go, I don't want to, although Tim might, and he'd probably be right, I wouldn't want to deny the possibility of something like that, but I at least would like to see some example of what would make that coherent. I haven't seen any yet.
So it's partly based on skepticism about...
Extreme skepticism, and also, just sociological. When people say that they're doing that, you ask them, they didn't mean it seriously. In any case, you could say, okay, I really want to do that ambitious thing. I doubt people are really smart enough to do that in a serious way, because I don't really think people are all that smart. I think we should limit ourselves to things which at least seem simple enough. It's hard enough to derive from Planck scale behavior of something in a discrete space-time, continuous behavior of the standard model and other stuff. If you're going to now talk about some purely algebraic framework which involves nothing like space-time, and then from that you're going to tell me space-time behavior is going to emerge, things are going to be going off the rails and all over the place, I can assure you of that. Yeah, Dave.
Yeah. Just ask a kind of more mundane example here. I mean, as you know, there's a hundreds of year old tradition in physics of wanting to know whether space-time or space more often should be the starting point in which matter exists, or whether what we actually have as a starting point is relations between the material bits and the space is a kind of fiction way of describing that. I mean, I think the philosophical case, the formal way of going is more sensible, it's quite a strong case, but I'm just interested, do you think in addition to that, that something like that kind of classical relationist idea is too abstract?
No, I don't. I think that various sorts of relational ideas could be perfectly compatible. So I mentioned discreteness this is in a different direction. That's a dramatic difference, but one which is not problematical. So when some people talk about emergence, they mean that. You could also have other kinds of dramatic changes of how we think about space-time, which might still not be such as to remove it from the realm of feasibility. So there are all kinds of possibilities. So that's why I keep mentioning algebraic. When somebody says it's purely algebraic, then I know they're talking about something that I have no clue what they have in mind. Yeah?
So just wondering whether or not your picture of the architecture of fundamental physical theory can countenance or can make room for sort of like strong emergentist positions, right? Positions that have been dubbed ontological emergentist positions.
Exactly.
Where the idea is you have these levels which in some strong and robust sense emerge from a lower level, and yet at the higher level you've got laws, and you've got a kind of, some people argue on the basis of considerations having to do with predicate indispensability and other arguments, that at this higher level you really can't understand it in such a way that it's reduced by functional analysis or something akin to that to the lower level.
It sounds to me like something, what you're describing is something I'd be pretty unsympathetic to. Not as unsympathetic as David might be. More unsympathetic. But I mean, because I think these people have in mind something really too strong, and
So you're saying...
I mean, it's a bit vague, so I'm not sure I totally understand the exact view, and I know there's lots of room for speaking at cross purposes here. But what I sense in what you're saying is that's not something I like.
People like Robert Laughlin, for example, have this high and lofty view of condensed matter physics, and they want to say, look, there are laws, fundamental physical laws governing what's going on, what we're describing in condensed matter physics, and there's a sense in which the phenomena we're observing and studying cannot be readily reduced.
Well, they can't, but readily reduced is one thing, but if they say there's something there's a fundamental gap between the levels, that's what I would resist.
Yeah, and he's saying there is this kind of ontological gap.
Well, then I'd have to understand better what he means by that. What is it? Because some people, like Freeman Dyson, would say, what the hell are you bothering me with the measurement problem is? I'm talking about different levels of description. Well, I mean, there's a macroscopic level, a microscopic level. What's all this reductionist craziness?
I mean, one way to understand it is just to say that the gap in your story of reducing this higher level from the lower level isn't really epistemic. It's an ontological metaphysical gap. It just can't be here.
Anyway, I'm not sympathetic. Yes?
Well, this isn't about that. Is it okay for me to make a comment that has nothing to do with this?
You can make a comment that doesn't do with anything.
Okay. Well, it has to do with the whole 2 hours. So I just thought, as we're drawing near lunch, I would add a comment, which was, especially for the students who have never seen, Bohmian mechanics really before, and they think that and it looks so obvious, and so you think, well, what's going on? How could, history have ignored this option? There's got to be something wrong with it. It looks like it's adding all this stuff, and wasn't there something, something sneaky or suspicious going on here? And I think it's sometimes useful to think about, the fact that, you can put classical mechanics, classical statistical mechanics in, so Koopman did it, von Neumann did it in a Hilbert space. You can mimic, like 99% of the quantum formalism for classical mechanics. And so you have a ray in a classical Hilbert space, rotating around. You've got so you've got a classical wave function. You've got a classical collapse. You've got a classical counterpart of the Born rule. You've got, you can do almost all of it. Right?
Yeah.
So, and then you can imagine, some kind of bizarro world, where, Bohr and Heisenberg and von Neumann's great-great-great-great-grandparents were English gentlemen and lived before Newton and came up with, the operator formalism of classical mechanics. And then, it was empirically adequate and it was good. But there are all these questions about, when does a measurement happen, and all these words used and all of that, and it's all unclear. And then Newton would come along and give a dynamics for what are the measurements about in this classical operator theory? What are the measurements about? And then you can imagine Newton coming along and saying, well, they're about particles, and they're about particles that behave a certain way, and then giving a dynamics for these for this ontology. And then half of the objections to Bohm's theory would then be would be objections to Newton in that bizarre world.
Very nice. By the way, a lot of, I think, not a lot, but I've encountered some physicists who, when they learn of Koopman formulation of classical mechanics, they say, then I understood classical mechanics for the first time. Yeah. Okay. Good. When do we start? How much time?
I would say 10 more minutes.
Yeah, okay. So let's see. One remark. I said the basic variables shouldn't be too abstract. Particles, position, fields on space. Too much abstraction can be a problem. In saying that, I'm not speaking about all elements of the theory, but just the primitive ontology. You could have other levels at a very high level of abstraction, which are playing a role governing the behavior of the basic variables, like the wave function, which is a pretty abstract thing. Like the wave function governs the behavior of the particles of Bohmian mechanics. I'm making here a distinction between a pure wave function ontology, they would be talking, and a wave function as part of an ontology which has involving local vehicles. Involving some local vehicles.
I mean, I guess the wave function there makes the point that you don't just want space and time, you want local objects in space and time.
Absolutely.
If I want to think about the wave function in space, I can. It just has to be one local. It has to attach a complex number to entries in space or something.
Yes. No, I mean in space. I mean configuration space. See here, this was part of a discussion relevant to David and ours. The red stuff. See, what I was doing in this part is giving you my conception of what the phrase AFT? architecture of fundamental physical theory. The red stuff is not part of that. Decoration, you've got a decoration of space-time. That's a crucial part. I don't want to say no. You've got laws. You've got ontology. You've also got laws. How are laws conveyed? They might be given in terms of differential equations, Newton's equation, maybe partial differential, ordinary differential equation, like Newton's, partial differential equation, like Schrodinger's equation. You could have stochastic processes given by stochastic differential equations or diffusion equations, stochastic laws, after all. Could be given by a variational principle, and you could even have a variational principle governing stochastic laws, like in stochastic mechanics. Or something else, God knows what. You've got a law, pretty broad concept. So here's my summary then of what's involved in the architecture, from my point of view, and many people's point of view, fundamental physical theory. We've got a primitive ontology of local fields. The positions of the particles with their positions in Bohmian mechanics is the simplest example. You've got a set which I call it strict X. These are decorations of space-time built out of the local variables based on the primitive ontology. It's a set of kinetically possible space-time histories of the primitive ontology, given by world lines, maybe a field over space-time, maybe a gravitational field over space-time, well, maybe lots of different kinds of things over space-time. Broadly speaking, a decoration of space-time, that's X. The kinematically possible. Then you've got a law which selects from the kinematically possible set the special things which obey the law. Most broadly speaking, you might say, what the law is a certain subset of the set of matter, is conveyed by, corresponds to a certain subset of kinematical possibility. And then, in order to get to extract predictions, you're going to need a notion of a typical space-time history, given perhaps by a probability measure on the set of histories corresponding to the law. In Bohmian mechanics, given by psi-squared probabilities on the initial configurations of the universe and the histories which flow from that. Now, there's a certain contradiction in what I just said, because in the case of stochastic laws, the situation is a little bit different. So I lied a little bit here. Here's the stochastic case. For a stochastic law, there may not be a separate set of histories that obey the law. Rather, in the stochastic case, instead of a probability measure on the set of histories that obey the law, might have to be replaced by a probability measures on the set of all kinematically possible histories. So that these two different parts, 3 and 4 here, might get thought of as being merged into one separate thing, where the measure of typicality is doing the work of typicality and conveying and the aspect of law at one and the same time. From a Humean point of view, this is no problem whatsoever. And from a from a non-Humean point of view, that's how I would think about stochastic laws. So typicality, in the case of stochastic laws, plays a really crucial point. It is the whole ball game. And gosh, I even got to part 3, typicality. I skipped some stuff. Here's a long quote from Boltzmann, who talks about typicality. This would be very relevant to Tim's talk, but I don't think I have time for that. Let me just give you some history. This is from Glenn Schaefer, who wrote about when did Cournot's principle disappear and the sources of Kolmogoro's Grunbeck riff. So these quotes are from the work of Schaefer. So these are very early references, not uses of the word typicality, but struggling towards the notion of typicality. Let me just read them. Jacob Bernoulli and Ars Conjectandi, really a long time ago, he says, because it is only rarely possible to obtain full certainty, necessity and custom demand that what is merely morally certain be taken as certain. The guy had to really be worried about somebody to say that. He was. Those of you who know about the large law of large numbers and its relation to attempts to understand probability have some idea of what he is talking about. Those of you who don't know that, this would require more explanation. There's definitely not time for it. Here's Cruz, the principle was named after him. Here is what he said. Also a funny statement. A physically impossible event is one whose probability is infinitely small. Infinitely small means really, really small, but not zero. This remark alone gives substance and objective and phenomenological value to the mathematical theory of probability. A strange but strong statement. Ah, good, you put your hands on your head. You should. Here is Paul Levy. Cournot's, this is much more recent. Cournot's principle is the only connection between probability and the empirical world. He also says, he calls it, this Cournot principle, the principle of the very unlikely event. Hadamard called it the principle of the negligible event. Kolmogorov, in his famous book on the foundations of probability, talks about probability throughout almost the entire book only as a mathematical concept. There is only one small section of the book where he worries about the connection between probability and the real world, because he knew what he was doing and he knew what he didn't want to get into. And in that section, because he can do the mathematics and it's beautiful and nice and powerful, and the question of the connection to the real world is really tricky and difficult and puzzling. In that, but he does try to make some use of it. In that section, it's called the relation to experimental data. He says only Cournot's principle connects the mathematical formalism with the real world. And Borel in 1948. The principle that an event with very small probability will not happen is the only law of chance. These are all statements about the importance of typicality. Here's more recent history where the word typicality is actually used. And the first place where it's clearly being used in the relevant sense that I know of is in Everett. Do you know of any earlier place? Let me read. In order to establish quantitative results, we must put some sort of measure, weighting on the elements of a final superposition. This is necessary to be able to make assertions which hold for almost all of the observer states described by elements of the superposition. We wish to make quantitative statements about the relative frequencies of different possible results of observation, which are recorded in the memory, and for a typical observer state. But to accomplish this, we must have a method for selecting a typical element from a superposition of orthogonal states. The situation here is fully analogous to that of classical statistical mechanics, where one puts a measure on trajectories of systems in the phase space by placing a measure on the phase space itself, and then making assertions. You heard all about this, which hold for almost all trajectories. Here, by almost all, he means the overwhelming majority, not almost all in the technical mathematical sense. This notion of almost all depends here also upon the choice of measure, which is in this case taken to be the Lebesgue measure on the phase space. Nevertheless, the choice of Lebesgue measure on the phase space can be justified by the fact that it is the only choice for which the conservation of probability holds, Liouville's theorem, and hence the only choice which makes possible any reasonable statistical deductions at all. One might quibble a bit about how strongly the word justified should be regarded there. Bell, then for instantaneous macroscopic configurations, the pilot wave theory gives the same distribution as the orthodox theory, insofar as the latter is unambiguous. However, this question arises: what is the good of either theory, giving distributions over a hypothetical ensemble of worlds when we have only one world? A single configuration of the world will show statistical distributions over its parts. Suppose, for example, this world contains an actual ensemble of similar experimental setups. It follows from the theory, talking about quantum mechanics, that the typical world will approximate realizable quantum mechanical distributions over such approximately independent components. The role of the hypothetical ensemble is precisely to permit definition of the word typical. Okay. I could skip that one and go to skip all of the statistical mechanics stuff because I want to come to the end. And there was a remark here about appeal. Well, no, I do want to say this. Here's an important, something which might be worth bearing in mind. Typicality not given by probability. Typicality is normally given by probability. You have a probability measure, but you only use it for a limited purpose. To say what has small, very small probability and what has big probability. You want to know what you want to have a sense of. Most, overwhelming majority, detailed probabilities with respect to that measure of typicality, 3/4 or 1/4 and so on, or don't have much meaning. What's meaningful is large and small. But it's convenient to use a probability measure for that purpose. But if indeed what's really important is large and small and not a detailed thing, then the usual rules for probability are not absolutely essential. I don't know what the usual rules for typicality are, but they should be weaker than the usual rules for probability. And various people have proposed, I think there are always versions of quantum mechanics, where they weaken the notion of probability to just a notion of typicality to try to come up with a version of quantum mechanics, where the problem which arose with the version they had was that what they were calling probability didn't satisfy the usual rules of probability. But once they recognized they only needed typicality, they said, okay, maybe we're in business here. So Mary Gell-Mann and James Harwood did that when probabilities as arising from their decoherent histories were problematical, but they would not necessarily be problematical regarded as just providing typicality. Bruno Galvin had the typicality-based version of quantum mechanics. And Sorkin and Dowker in their co-event formulation of quantum mechanics very emphatically say that they were influenced by Cournot's principle to overcome their problems by appeal to typicality instead of insisting on probability. So, since typicality does provide you with a certain amount of flexibility, it might be a good idea to actually take the notion really seriously as something transcending probability and trying to come up with new physical theories. One last, there's a long remark about typicality. It's used all over the place, and this is a long, well, we have 1 minute, 2 minutes, 3 minutes?
We have 3 minutes.
Good, let me try to read this remark. This is about a general remark about appeal to typicality from a paper that I wrote with Joel Leibowitz, Roderick DeMolka, Dino Zangi, about Boltzmann's quantum ergodic theorem, which is an ignored theorem, maybe partly because it was in German, partly because the result was a typicality result, which is something not so easy to understand. He says, we say, not he, we say, when applying the method of appeal to typicality, one usually uses the language of probability fit. But that does not imply that any of the objects considered is random in reality. Rather, it means that certain sets of wave functions of orthonormal bases over the have certain sizes, for example, close to 1, in terms of certain natural normalized measures of size. That is, one describes the behavior that is typical of wave functions or orthonormal bases. However, since the mathematics is equivalent to that of probability theory, it is convenient to adopt that language. For this reason, using a normalized probability measure mu does not mean making an assumption of equal probability, even if one uses the word probability. Rather, it means that if a condition is true of most, whatever, like for example, sometimes you consider different possible Hamiltonians, you have a measure on Hamiltonians, and see what will happen for the different Hamiltonians. Something is true for most Hamiltonians H. This fact may suggest that the condition is also true of a concrete given system, unless we have reasons to expect otherwise. Of course, a theorem saying that a condition is true of the vast majority of systems does not prove anything about a concrete given system. If we want to know for sure whether a given system is normal, that had precise meaning in our paper, but just take it to be some good thing, normal. We want to know whether a precise given system is normal for every initial wave function. We need to check the relevant condition. Nevertheless, the typicality theorem is, as we have suggested, illuminating. At the very least, it is certainly useful to know which behavior is typical and which is exceptional. The method of appeal to typicality belongs to a long tradition in physics, which also includes Wigner's work on random matrices in the 1950s. In the words of Wigner, one deals with a specific system with its proper, though in many cases unknown Hamiltonian, yet pretends that one deals with a multitude of systems, all with their own Hamiltonians, and averages over the properties of these systems. Evidently, such a procedure can be meaningful only if it turns out that the properties in which one is interested are the same for the vast majority of the admissible Hamiltonians. This method was used by Wigner to obtain specific, new, and surprising predictions about detailed properties of complex quantum systems in physics. Finally, if we know of a given system that its Hamiltonian H belongs to a particular small subset S0. Imagine a big set S, of Hamiltonians. And imagine you have some natural measure over that set, so you can talk about most. Big set of Hamiltonians, then a small subset S0, really small subset of more physical Hamiltonians, more realistic Hamiltonians. Big set, small set. S naught is the small set. S is the big set. If we know of a given system that its Hamiltonian H belongs to a particular small subset S0 of the set S of all self-adjoint operators on the appropriate Hilbert space, then two kinds of typicality theorems are of interest.
Just about to end.
One saying that the relevant behavior occurs for most H at S0, for most of the physical Hamiltonians, most H in the small set. The other saying that it occurs for most H in the big set. Note that the former does not follow from the latter when S0 is very small compared to S, as it would then be consistent with the latter for S0 to consist exclusively of exceptional Hamiltonians. Nor does the latter follow from the former, so the two statements are logically independent. In fact, both are of interest because each statement has its merits. The typical theorem about S0, about the small set, the typicality theorem about the small set, gives us more certainty than about that the given system whose Hamiltonian belongs to S0 will behave in the relevant way. If you know something is typical for the small set containing what you're interested in, you should have more confidence about it being true for the actual physical Hamiltonian. The typicality theorem of the big set S gives us a deeper understanding of why the relevant behavior occurs, as it indicates that the behavior has not much to do with S0, but is widespread all over S. That is, there is a reciprocal relation. So here we have some complementarity. That is, there is a reciprocal relation. The greater the degree of certainty that a typicality theorem confers, the less its explanatory power. Thank you.